Today we're going to take a break from our typical geometry lessons and we're going to spend the next couple weeks looking at statistics and probability. So our first lesson is our intro lesson and it's Intro to Statistics. So throughout this lesson we're just going to talk about basic things. We're going to talk about what statistics are. We're going to talk about descriptive versus influential statistics, and we are going to look at mean, median, and mode. That's something you've done before. So just the overall basics of this course. So in general, statistics are a branch of mathematics dealing with numerical data. Statistics is the collection, presentation, interpretation, and organization of data. There are many different ways to organize statistical data. For example, we could be looking at charts, tables, graphs, spreadsheets, etc. So we're going to be looking at a variety of different statistical measures, but overall we're just going to talk about the general parts of this, and in future courses here at North Kingstown you will go further into statistics. The first part we're going to look at is descriptive versus inferential statistics. Descriptive statistics uses data to provide descriptions of the population, either through numerical calculations, graphs, or tables, whereas inferential statistics makes inferences and predictions about population based on sample of data taken from the population in question. And I have a short video clip that I'm going to show you that uses graphics and goes more into depth on these two terms.
Descriptive and inferential. Descriptive statistics describe what the data show. Descriptive statistics usually include things like where the middle of the data is, what statisticians call measures of central tendency, and measures of how spread out the data are. They take huge amounts of information that may not make much intuitive sense to us and compress and summarize them to hopefully give us more useful information. Let's go to the thought bubble. You've been working for 2 years in the local waffle factory. Day in and day out, you create the golden browniest, tastiest frozen waffles ever created. The holes are perfectly spaced, screaming for syrup. And now you want a raise. You deserve a raise. No one can make a waffle as well as you can. But how much do you ask for? An extra $1,000? An extra $5,000? You know you're valuable, but have no idea what other waffle makers get paid. So you dig around online and find there's an entire subreddit devoted to waffle makers, and someone, username Waffle Leaks, has posted a spreadsheet of waffle makers' salaries. Now, with a quick glance at this huge list of numbers, you can see whether the woman who works at a similar job at the rival frozen waffle company makes more than you. You can see how much more you're making than the new guy, who's just now learning to mix batter. But you still don't know much about the paychecks of your waffle company as a whole, or the industry, because it turns out there are thousands of waffle makers out there, and all you see is a list with data points, not patterns that can help you learn more about how much you might be able to convince the boss to pay you. Here is where descriptive statistics come in. You could calculate the average salary at your company, as well as how spread out everyone's salaries are around that average. You'd be able to see whether the CEO's paychecks are relatively close to the entry-level batter makers, or incredibly far away, and how your salary compares to both of their salaries. You could calculate the average salary of everyone in the industry with your job title and see the high and low end of that pay. And then, armed with those descriptive statistics, you could confidently walk into the waffle boss's office and demand to be paid for your talents. Thanks, Thought Bubble. While descriptive statistics can be great, they only tell us the basics. Inferential statistics allows us to make inferences. Clever namers, those statisticians. Inferential statistics allow us to make conclusions that extend beyond the data we have in hand. Imagine you have a candy barrel full of saltwater taffy, some pink, some white, some yellow. If you wanted to know how many of each color you have, you could count them, one by one by one. That'd give you a set of descriptive statistics. But who has time for all that candy counting? Or you could grab a giant handful of taffy and count just those you've pulled out. which would be using descriptive statistics. If your candy was, in fact, mixed pretty evenly throughout the barrel and you got a big enough handful, you could use inferential statistics on that sample to estimate the content of the entire taffy stash. We ask inferential statistics to do all sorts of much more complicated work for us. Inferential statistics lets us test an idea or hypothesis, like answering whether people in the US under the age of 30 eat more fast food than people over 30. We don't survey every person to answer that question. Let's say someone tells you that their new brain vitamin, SmartyVite, improves your IQ. Do you rush out and buy it? What if they told you that the average IQ increase for Group A, 20 people who took SmartyVite for a month, was 2 IQ points, and the average IQ increase for Group B, 20 people who took nothing, was 1 IQ point? How about now? Still not sure? It's a pretty small difference, right? Inferential statistics give you the ability to test how likely it is that the two populations we sampled actually have different IQ increases. However, it's up to you as an individual to decide whether that's convincing or not. And don't be alarmed if the bar you set isn't the same in every situation. It's entirely okay to have different standards for the questions, does my cat like Fancy Feast more than Meow Mix, versus does this drug cure lung cancer? It might take more evidence to convince you to take a new, supposedly cancer-curing drug than to switch cat food brands. It should take more evidence to convince you to take a new, supposedly cancer-curing drug than to switch cat food brands. With inferential tests, there will always be some degree of uncertainty, since it can only tell you how likely something is or is not. Your job is to take that information and use it to make a decision despite that uncertainty. If statistics were a superhero, its bat call would be uncertainty, and its tagline would be, when you don't know for sure, but doing nothing isn't an option. Statistics are tools. Statistics help us make sense of the vast amount of information in the world. Just like our eyes and ears filter out unnecessary stimuli just to give us the best, most useful stuff, statistics help us filter the loads of data that come at us every day. Descriptive statistics make the data we get more digestible, even though we lose information about individual data points. Inferential statistics can help us make decisions about data when there's uncertainty, like whether SmartyVite will actually increase your IQ. But statistics can't do all the work. They're here to help us reason, not to reason for us. They can help us see through uncertainty, but they don't get rid of that uncertainty. To push our tool analogy a step further, statistics, like chainsaws, are pretty useless, even dangerous, without understanding how they work. We need to know how to use them and how not to use them.
Next, we're going to take a look at statistical measures, or measures of central tendencies. So a measure of central tendency describes a set of data by identifying the central position in the data as a single value. The three most common measures are called mean, median, and mode, which most likely you have all seen before. So mean is the most commonly used measure. The mean is the sum of all of the values divided by the number of values. Here's your equation to find the mean. The median is the middle value in an ordered data set. So you put all of the numbers in order, you order them from least to greatest, and you locate the middle value. If the number or value is even, the median is the average of the two middle values. And lastly, we're looking at the mode, and the mode is the value that occurs most often in a data set. To determine the mode, order the values from least to greatest and locate the value that occurs the most. You can have no mode, or you can have multiple modes. So don't be confused if you have more than one number. Let's take a look at the first example. So in my first example, we need to calculate the mean, median, and mode for each data set. Let's start by looking at the mean for number 1. So the mean is when we add up all of the values and then we divide that by the number of values. So if we add these numbers together, we would add 2 plus 2 plus 2 plus 2 plus 2 plus 5 plus 5 plus 6, and that's equal to 32. So we have the sum, which is 32, divided by the total. And when I just added those together, I added 9 values total. So 32 divided by 9, when I divide that out, it's approximately 3.556. So approximately 3.556 is going to be the mean. Next, let's look at the median. The median is when you organize your numbers from smallest to largest. When we do that, we would have 2, 2, 2, 2, 2, 5, 5, 6, 6. And for the median, we would take this, we would eliminate them until we get to the middle number. So in this case, your median is 2. And lastly, mode. Mode is the number that occurs most often. I think this data set, it clearly shows which number occurs most often, and that would be the number 2. So our answer for mode would be 2. For number 2, this one I gave you a table of values and it's a group of test grades. So before I even start with mean, median, and mode, what I'm going to do is take a moment and organize this data. So I'm going to take a moment and list this from smallest to largest, including all of the numbers in this table. So I have 65, 75, 77, 80, 82, 85, 85 again, 87, 95, 97, 100, and 100 again. To find the mean, we're going to sum all of the values, so add up all of these numbers. I just did that. It came out to 1,028, and the total number of values that we have is 12. When I do 1,028 divided by 12, it comes out to approximately 85.67 for the mean value. The median is the number that's directly in the middle. So let's take a moment and cross off our values. We end up with a median between 85, or between two numbers. In this case, both numbers are the same. So our median is just going to be 85. But suppose those two numbers were not the same. If that happened, then you would need to find the average of the two numbers. So add them together and divide them out. And lastly, the mode. The mode is the number that occurs multiple times. In this data set, we have 85 that occurs twice, and we have 100 that occurs twice. So this is called bimodal because there's two modes, and I'm going to list both of them. We have a mode of 85 and a mode of 100. So in parentheses, I'm just going to write two modes, and two modes indicates that it's bimodal. Not that you need to memorize that or anything, it's just good to understand that it's completely normal or completely fine to have multiple values of the mode. In different situations, some measures become more appropriate to use than others. We should use mean, or using the mean is most appropriate when the data does not have outliers. If you have a very close set of data, all the numbers are very close together, it's appropriate to use the mean. You should use the median when the data has outliers. There are no big gaps in the middle of the data though. So you might have one number that's really big or one number that's drastically smaller than the rest, but the rest of the data group is pretty tight, so the numbers are pretty close together. That's when you want to use the median. And the mode is most appropriate when you have a set of data that has multiple sets of repeated numbers, or it has many of the same repeated number. That's when you want to use the mode as your data set. So moving on to the next set of examples, we need to choose appropriate measures. So we need to use that table that I just went over, and it has highlighted values, so when you're using each one. We need to determine which measure of central tendency best represents the data. So number 1 says the table shows the number of medals won by the US Summer Olympics team. Which measure of central tendency best represents the data? Then find the measure of central tendency. So we're looking at the number of medals. That's specifically what we're looking at. So it looks like in year 1992, we won 112 medals, 96, 101, 2000, 97, 04, 103, 2008, 110. So I would say that since this data set has no extreme values or numbers that are repeated, then the mean would be the best representation of the data. And I'm just going to drop in my answer right here, which kind of explains why I would use the mean. So here's my description of the reason why I would choose to use the mean. And once I find the mean, I end up with 523 over 5, which would divide out to 104.6 as my mean value. For the next example, the table shows the average lifespan of some animals. Which measure of central tendency would best describe the data with and without the outlier? Justify your selection. So if we look at this table over here, we want to analyze what we have. So we see that we have numbers 35, 30, 50, 200, 30, 70, 200, 30, 70, and 20. So I see that there's one major outlier, and it's the Galapagos turtle, which its lifespan is 200 years. Everything else is relatively close, but that is definitely one that stands out. So that is called an outlier. So what I did was, just to save us a little time, instead of going over the same thing over and over here I left the number 200 in, and I typed out what the mean, median, and mode would be. Then I took the outlier out, so without the outlier, so I removed the number of 200 completely. I just crossed it right off the list, and I found the mean, median, and mode. And then I analyzed what I'm looking at. So between the two values, I see that the mean was 62 with the outlier, and it was 39 without the outlier. Those are drastically different. I see that the median was 35 with the outlier and 32.5 without the outlier. So that was pretty close. Not that different as far as the life expectancy. That's about 33 years versus 35 years. That's close. And the mode didn't change at all, so the mode was the same. So the biggest difference we see with the outlier is within the mean. So right here I wrote a note for you, and it says the mean was affected the most with the outlier. The median changed very little with and without the outlier, so it best describes the data in both cases. The mode does not describe the data very well, since there were only 2 repeated numbers. So because there wasn't a large set of repeated numbers, you just don't really want to use the mode as your best measure of central tendency, which leaves the mean or the median. But the mean was drastically different with or without that outlier. So therefore, the median, which hardly changed, would be our best representation of central tendency. And it might take some practice to get used to what I'm talking about with these, but the biggest hint I can give you is just use this chart. So do you have data that has outliers? Do you not have outliers? Do you have data that has a lot of repeated numbers? Do you have big gaps? Like, which one of these fits your data set the best, and that's the one you want to go with. All right, the last part of the notes is the range, and range is something that you've done before as well. So the range is the set of data that's the difference between the greatest and the least value of the set. A large range indicates that the data is spread out, and a small range indicates that the data is close in value. Let's look at number 1, and then I'm going to have you do number 2 by yourself. Number 1, we have the data set 2, 5, 6, 2, 2, 2, 5, 6, 2. So I ordered the numbers from smallest to largest, and in order to find the range, what I did was I looked at the largest number of 6 and the smallest number of 2. I subtracted those to give me the range of 4. 4 is my final answer for the range. Number 2 is not organized in order, but I would like everyone to find the range. So what's the highest number, what's the smallest value or smallest test grade, and find the difference between the two. Okay, hopefully you did this by yourself, but the range would be 100 for your largest test score, minus 65, which is the smallest test score, and that gives you a range of 35. So the distance in test score points varied 35 points. I would like everyone to complete the on your own section by yourself. I think that this stuff is mostly repeated from previous concepts you've learned, but also we went through quite a few examples. So please try the on your own section by yourself, and then come back to the video if you would like to check out my answers.